This week's problem of the week is called an additive ski trip, where our triangle represents a ski slope where all the skiers start at the top, the 4, and head down the triangle. Each time they hit a number, the skier must decide to go right or left to the number below. The goal is to get to the bottom with the smallest sum possible. People who have done problems like this before may have guessed that perhaps there's a relationship between this triangle on the left and a triangle on the right that many of you may recognize is known as Pascal's triangle. In Pascal's triangle, each number in the triangle represents a number of different routes that are possible to get to that number. So for example, to get to the 5 in the lower left, there are 5 different routes, and they are shown here. Well, back to our problem, you can see we have to go down to the row at the bottom, and it's 1 plus 5 plus 10 plus 10 plus 5 plus 1, different ways. That adds up to 32. Quite a few to do them all, but at the problem of the week, we leave no stone unturned. So we found a problem of the week intern who typed all 32 ways in on an Excel spreadsheet. And here they are, and the lowest sum is marked there with the red arrows. It's 26, and there is the route that it takes to get there. But you might guess that if we ask you to do another problem with more rows, one more row would have 64 different ways. One more row after that would have 128 different ways. So you might ask, is there a shorter way? And yes, Dr. Bardot points out that you could make a triangle using minimum partial sums. And here's a start. In the one on the right, the reason there's a 9 and a 10 there is the 9 represents the sum of the 4 and the 5, and the 10 represents the sum of the 4 and the 6. So in the next row, the 16 in red, we have a choice. The red route, the sum is 16, and the green route, the sum is 17, so we choose the red route. And then we fill in the rest of the minimum partial sums, and you will see there's a 26 on the bottom, and that is the answer to this week's problem of the week.